The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everybody, and welcome to the CATIA Analysis webinar. My name is Auday Arawi from Intrinsic Limited. I'll be joined by my colleague Amit Patel for the next hour or so to give an overview about the FEA analysis tools available for CATIA users. I'd like to start by giving an introduction about the presenters today. I'll start with myself with postgraduate degrees in mechanical engineering, welding technology, design and simulation. In the last 16 years, I have worked for a number of simulation software vendors and resellers developing design and simulation processes. And during the last 3 years at Intrinsic, I've helped Intrinsic's clients with their design requirements through account management. My colleague Amit, he has a BEng in aircraft engineering and MSc in aerospace vehicle design. Amit has worked at Intrinsic for the last 3 years, and he has a senior role in delivering design projects as well as being one of the leading trainers at Intrinsic. Okay. If you haven't heard about Intrinsic, perhaps this is the chance to do so. Intrinsic is an engineering company founded in 1998. The primary service that we offer is PLM solutions. We are a leading VAR for DASA system and basically provide software solutions such as CATIA for design, Innovia for data management, Simulia for simulation, XLead for search and search-based applications, as well as Delmia for manufacturing simulation. The other part of the business basically do engineering consultancy services, in particular offering design and structural analysis services. So generally, Intrinsic basically offer support, training, and engineering services. We have 3 sites worldwide, 2 of them in the UK and the 3rd one in South Africa. The UK sites are in Milton Keynes and Castle Donington, and the South African one in Johannesburg. With about just over 50 employees at Intrinsic, and makes the total about 200 within the Intrinsic group. Okay, perhaps this is the stage that we would like to get feedback from the delegates. You will see a question coming on the screen. If you don't mind, if you could answer it by choosing yes or no. Basically, the question is, have you used FEA analysis before? Just so we can get some background on the people attending today. Excellent. So it's feedback coming at the moment. And it's looking good. So far, it's about almost 90% of you have used FEA and 10% haven't. So that's good news. Okay, so really that shows that a lot of people are actually aware of FEA benefits these days. So that's encouraging. Okay, excellent. The agenda today basically is going to include the following. We will start by giving an introduction. We will give an introduction about what is FEA, just in case you're not familiar with FEA. Then we can go about exploring why we recommend that you use CATIA analysis. Then we begin our first session about exploring all the FEA analysis tools for linear analysis within CATIA. This would be complemented with very nice video demonstrations. Then we go into the second session of this webinar about exploring non-linear analysis tools available for CATIA users. Again, we'll be complementing that with some very nice demonstrations. And finally, we will go into our final part of the webinar, which is exploring the latest development from DASA system, which is the 3D Experience platform. Okay, and finally, we leave some time, hopefully, for any questions from delegates later on. Okay, so let us start. What is FEA? I do apologize if you find this quite trivial. Some of you may have already used FEA for years and very experienced, but generally speaking, FEA is the simulation process to calculate how a component or a structure responds to a load. So usually gets used when things get too complex and theoretical solution cannot be easily obtained, or sometimes experimental testing becomes very expensive. How does it work? Again, if you want to put it in a simple way, the structure is broken into finite number of elements or regions called elements, usually surrounded by nodes, and basically the properties of each individual element is calculated, and finally the property of the entire object of the structure obtained by combining all these elements together. So really the major application for it allows you to reduce the amount of physical testing. It doesn't actually stop. It doesn't mean that you cut physical testing 100%. It always comes as a complementary and allow you to reduce the amount of it, because it's always good to use physical testing to do validation of FEA stuff. In terms of what it gets used for, almost any engineering application find application for FEA, whether it's transportation, mobility, aerospace, marine, industrial equipment, high-tech, consumer, life sciences, which is really very interesting application, which come up quite a lot in the last few years. We find that a lot of high technology these days being developed to look at life sciences. There's so much application for modeling, for example, human parts. There's a lot of development in being able to model human tissue materials and so on. So that's quite interesting, and the future is quite bright in there. Energy applications, architecture engineering, and many, many other applications. What can it tell me, or what can it tell people? Usually answers many questions. A typical question: how can I improve my design? Will my product leak? Will it break if I drop it from certain heights? How long will my product last? How will it perform if it's used off-spec? All these questions can be answered easily by FEA. How can I make my product lighter? Is my product safe? Will my product pass or require certification testing? If I make my product from cheaper material, will it still work? Okay. So just so we can summarize what sort of advantage FEA can offer us, it's cost effective. As you can imagine, physical testing are getting very expensive, especially if you have to do many different iterations. So there's no need to create the real test and destroy stuff and so on. Time saving. Again, once you created a simulation, you'll be able to read, change the parameters very easily without having to go to the factory and redo prototypes and stuff like that. So a lot of time saving in it. Speed up to market. So again, once you've done that, you'll be able to get the product right to the market quicker. Optimization, very easily done by changing parameters within the simulation process. Then you can get the answer quicker. Multiphysics, if you're doing advanced analysis, you'll be able to couple different type of analysis behaviors, such as thermal and stress, or thermal and CFD, and so on, fatigue analysis, all that kind of things that you could do with multiphysics. So in terms of what is so special about CATIA for FEA analysis, the strongest part basically is integrated with CATIA. So that's, you find this is really, really useful, because it's using the same user interface that you used to for design environment, okay? And it's all the analysis specification are associated with the design. So any changes, it gets maintained in there. You don't need to come out of the software. And basically, you can properly size the design, add material only when you need it, basically. The next part, which is it offers you realistic and robust modeling. So for example, if you're doing hybrid assemblies, if you're dealing with solids, shells, or wireframe, if you're dealing or combination of all of them, you can still do that. It also allows civil design. If you work in an assembly, you'll be able to all work on the same assembly. And also allows you to model a lot of connections, such as bolts and contact and welds, which means you can create the model very quickly in no time with any facility within the design capability. If you want to compare the design alternative, for example, if you have a number of parameters that you'd like to test, rather than go to factory and create prototypes and all, you can actually parameterize your model like such as a geometry parameters, whether it's length or diameter or width and so on, or if it is material properties that you'd like to change in order to get the best one, or change the mesh parameters or loading parameters. All these things can be parameterized. You can also optimize the structure using the product engineering optimizer. With this one, you'll be able, for example, to minimize mass or maximize stiffness, or control basically how stress and displacement behave. This is a very interesting one, which is basically the workflow for designers. It allows you to use templates. And this templates basically can be customized by, for example, senior designers for junior designers to be used later on. So they could maybe create templates to control mesh properties, or could be connections or load constraints, or even reports. When you generate reports, you could set up certain templates to generate reports, and in the future the junior designer just come and use these templates to use it for his project. And the final one, basically, to get confidence in the results. So it allows you, because there's so many automated tools, such as automating the mesh, all that kind of things allows you to get the software do all the hard work, basically, in order to work out, for example, the best balance between solution accuracy and cost. Perhaps at this time, I'd like to invite my colleague Amit to come in. So it's over to you, Amit, please.
Okay, thank you, Alday. So hello guys, I'm Amit Patel. So I'll be talking to you about the types of analysis that we can perform in CATIA V5. We'll also have a look at some of the additional add-ons, so the other types of analysis that we can perform in CATIA as well, so with some add-on packages, before passing it back over to my colleague. So we'll begin by talking about linear static analysis. So I apologise if this is a bit elementary for some of you, but it's one of the simplest forms of FE analysis, so linear analysis or linear static analysis, basically however you like to call it. It basically allows the user to calculate displacement, strains, stresses, reactions, forces, etc., etc. But due to the nature of the analysis, the assumptions are that the translations, stresses, strains are small, essentially. Okay. We also assume that the material doesn't yield, so and the material properties are independent of time and temperature. So if you want to analyze a material stress with respect to time, it wouldn't be a linear analysis that you'd be performing. Okay. So basically, in simple terms, I'm sure everyone's familiar with the stress-strain curve, we're only really interested in the linear part of the stress-strain curve. So we're not looking at hyperelastic materials, which have a non-linear relationship. We're just looking at linear materials, so the linear part. So the other thing is we basically assume that the material deforms linearly. So the relationship between the deformation and the strain is proportional. Okay? So therefore, a linear analysis displays a stress value. If a linear analysis displays a stress value beyond the material's yield stress, we generally assume that yielding would have occurred and that the deformation at this point would be inaccurate. So you can see it's also heavily associated to Hooke's law. So analysis tools for linear analysis. So what solutions are there for CATIA V5 users? So we're going to keep coming back to this diagram. So you can see along the top we've basically got designer, design engineer, and analysis expert. We're going to start off by just focusing on the designer part of this diagram, which is just the CATIA V5 analysis tool. So we're looking at the designer just being able to perform linear static analysis and mode-based dynamic analysis. So we're not saying that analysis experts wouldn't be performing these analyses, it would just be the designer. We're just saying the designer wouldn't be basically creating like a transient dynamic load analysis, etc., etc. They'll be sticking to linear static analysis that they can perform. And again, this can be done using CATIA V5. So in CATIA V5 linear analysis. So it can be performed using parts and assembly analysis. So whether you have a part, whether you have an assembly, you can create a linear static analysis of it inside CATIA V5. Within CATIA V5, you need the GPS module to create a part structural analysis and a GAS module to create a assembly structural analysis, but these are all part of a GAE configuration. It also supports multiple topology. So what that basically means is if you had an analysis of an assembly, it doesn't all need to be solid. So if you want to analyze a solid, it would generate a 3D mesh. It doesn't entirely have to be three-dimensional. So you could have 1D geometry in there and create a beam element alongside 3D meshes and create connections between the two in order to analyze your model. So in this particular instance, what we've got is we've got a hub of a vehicle. We're analysing some stresses on the hub, and we wanted to model in the suspension component, so the upper and lower wishbone and the steering column. What we're doing, because we're not entirely interested in the wishbones itself, we're assumed that they have constant section. Because they have constant section, we can just create a 1D element. Why not use 3D? Because if we have the entire model with 3D meshes, it will just take way too long to analyze. So we're trying to simplify our model where possible. And again, at the bottom, we have a range of tools. So you can see at the bottom, there's many tools available for the user in CATIA V5 to create a linear analysis. So we've got a range of loads that we can apply, various different constraints, connections, etc. Okay, so this basically brings me on to my first demonstration. So this is actually a pre-recorded demonstration, which I'm going to narrate over the top of it. And it's basically a linear static analysis being performed on a mountain bike. The components that we're actually analysing are the frame, the shock absorber, and the bracket which attaches the rear of a shock absorber to the frame as well. And we're actually interested in the join from the top part of the shock absorber to the frame. So that bracket would have been welded or onto the frame itself. So we're trying to analyse that. So I've just talked you through this analysis. As you can see, it's just a mountain bike. We've got an assembly. And the first thing we're going to do basically is the frame itself is made up of multiple parts. So each part of the frame is in this assembly is an individual part. But just to make it simple in our analysis, what we're doing is it's just going to create an associative assembly part. So each item in the frame basically is seen as one part. So rather than have the top part of the frame, the left part of the frame, right part, etc., we're just creating the frame as one part. So again, you can see the associated part. Now what we'll do, we'll just assemble it all into one part body. So this is this is a must in CATIA, so it all has to be under a part body. So we've just created a Boolean operation. And then we're now going to apply a material. So we can apply a material at the part level or within the assembly, but in this instance, if we create the material to the part in the part level, that will automatically be ported over into the analysis when we move into it. The next thing we want to do, so what we're doing here now, is hiding components of the mountain bike that we're not interested in. So there's no point of overcrowding your analysis, making it longer to set up, making it longer to compute. You basically just want to eliminate anything that doesn't need to be in your analysis. Or that you could use something called virtual parts to replicate. Okay? So these are the four components I'm basically interested in the analysis. So I'll just move into the analysis workbench. So I'm going to create the analysis. Once it's let me into the workbench, there we go. I'm going to create a static analysis, a linear analysis. And you can see it's automatically created my mesh. So there's four meshes because there's four individual parts. And I can just modify the mesh size by just double clicking on the meshes. Okay. Then I can restrain my model. So I'm restraining the frame, so towards the front of the frame where the handlebars would go, and the rear of the frame where the seat post would go. So in this instance, I'm creating sliding constraints. And then because we have 4 parts, even though we've got 4 meshes, CATIA doesn't really know how they interact with one another or that they interact at all. So we need to tell CATIA that they're actually connected. So this is what we're doing now. We're creating connections between parts. So by picking the appropriate topology, so in this case, between the bracket that we want to analyze and the top part of a shock, create a connection. Another connection between the second bracket and the frame. Okay. So you have to take care when selecting the right topology. Then we have the lower part of the shock and the bottom part of the bracket. And then finally, the 4th connection is between the top part of the shock and the bottom part of the shock. So there we go. So now we've told CATIA everything's basically connected. We haven't actually told it how it's connected. So we've said there's a connection, but we haven't got the round to telling it what type of connection it is. So this is where we basically create a connection property. So all I'm doing is saying at the pivot points that there's a rigid connection, but it's allowed to rotate, so about its own axis. So that's what I'm doing in the 3 instances. There we go. So I'm allowing rotations. And then on the final one, I'm basically creating a fastened spring. So I'm allowing it to translate, so dampen along its own axis, but I'm making it infinitely stiff in the other directions, so it can't translate or in the other directions. So just basically acting as a damper would, it will be translating along its own axis. The next thing I'm going to simulate a force as if there's basically an impact on the rear wheel and the shock's absorbing the impact. So I've just applied a force on the bottom end of the shock. And now I've basically got all my mesh, my properties, my materials from the parts itself, and my loads and my restraints, etc. So I'm ready to compute. So I'm computing my analysis now. The linear analysis is fairly quick, so it won't take that long to compute. There we go. So there's my analysis results. And it appears that nothing's really happened, but what we need to do now is tell CATIA, well, what result do we want to see? So in this case, I've selected a displacement. I'm going to change how that displacement looks, so I can change the render style essentially. And there we go. So this is showing my displacement. I can then animate the analysis so you can see the deformation. So again, this isn't time-based. It sees deformation at 0 and then maximum deformation. It's just you just tell it how many steps you want to see in between, so it appears to animate, but it's not actually time-based. And now what we're going to do, we're going to create a measurement. So CATIA calls basically a measurement a sensor, and we're going to create a reaction sensor at the top bracket, so where the top part of the shock meets the frame. And then we're going to actually create a secondary linear analysis where we actually isolate that top bracket itself. So we're bringing it into another analysis, change the mesh size, restrain it, so we're clamping the top because it's fixed, or it'll be welded onto the frame. So essentially we're just assuming it's fixed on. And then we're going to take the measurement from our reaction sensor, okay, and actually input it into our secondary analysis as a force. Okay. So there's the results from our reaction sensor, so the components in the force in X, Y, Z, and then the moment around X, Y, and Z. And then we're going to create a bearing load on that where there will be a bolt between the top part of the shock and that bracket. And we're essentially going to input those reactions. Now if we compute that analysis, so we'll just run the computation. Okay, and now we can review the results. So we can see basically the stresses within basically essentially that lug. Okay, and animate it. So we've taken the results from one analysis and basically fed it into a secondary analysis. Okay, so as we saw, there's a range of tools to create forces in our forces, constraints, etc. in our linear model in CATIA V5, so linear analysis. But what we didn't really get to see is, well, all we did was just change the mesh size. So does that mean that we don't have really have much control over the mesh? That isn't actually true. So there are additional tools available for the user within the linear analysis to actually gain more control over the mesh. So these may require additional add-ons such as Nelfini structural analysis, FEM surface, FEM solid, and that will give basically the user more element types to play with. So we saw we had tetrahedral elements. Now we can have quad elements in our models. We basically have greater flexibility with modifying the mesh. Okay, and again, if we can reduce the degrees of freedoms, it basically results in a lower computation time. So that's basically our aim. So in this demonstration, I've got another one. So this is basically an aircraft surface model. Because it's symmetrical about the center axis, I've basically taken half of the model. So there's no point using more than you actually need. If it's symmetrical, only use half of it. If there's two symmetry planes, use a quarter of it, so on, so on. So we're always trying to reduce the computation time. Okay. So what this will basically demonstrate is basically using advanced meshing tools. So this is available as another workbench. So if you have the Nelfini add-on, for example, it will give you access to this workbench. And we're going to have a look at matching mesh seeds. So in this instance, what we're doing, we're going to first of all mesh our basically the ring ribs. Okay, so that's going to dictate, that's the first item we're meshing. You can see the seeding on there. Just run the mesher, and you can see the mesh on the wing ribs. So at this current stage, doesn't really mean much to us. We're not really focusing on the size of the element, so it doesn't really mean much. It's because we haven't got any meshes to match against. So now in this instance, what we'll do, we'll go and mesh the aerofoil surface, but don't forget, we need the elements to line up with the ribs. So the reason we want to do that, we want to reduce the number of nodes we have in our model. So if we can share nodes between elements, then we can go ahead and do that. So what we're doing in this instance, where we're meshing the top surface of the aerofoil, we're basically telling it will actually match the seeding, so it matches the wing ribs and also matches the spar. So now when we run the mesh, just compute it. So there we go. So since we selected the wing spars as well, you can see that the seeding also creates a point where the intersection is as well. Take a sec to run that, and there we go. So now we've got the mesh on the actual aerofoil surface, and you can see it creates nodes. Well, it's actually sharing nodes, so you can see that the elements all meet up at a neighboring node. Sorry, at a common node. Okay. What we can also do with the advanced meshing tool, so if we've already created a mesh and we're not really that happy with it, we can actually modify the mesh as well by hand. So you can see in this instance, I can pick a node and just remove nodes, manually manipulate nodes along the surface of the actual aircraft surface. So you can see if there's any areas I don't like, or if I want to refine, I can refine it. So all I'm doing in this case is splitting up a certain area, and then I'm going to refine the mesh within that boundary. So it gives you a lot of control over your mesh itself. And it updates all the elements around it, so the seeding matches at that boundary as well. Okay. So you can see we don't really have to do much to get CATIA to do what we want as well. We just tell it and it does it. Again, we can simplify meshes. So you can see in this instance, there's a node I don't like, so I can just drag it. Okay. If I just want to manually move a node, I can do that. And it just updates the mesh around it for us. So the best thing about CATIA is it's pretty difficult to get a mesh that won't work, essentially. And there we go. If we speed it up a little bit, let's assume that that symmetrical part of the aircraft is now mesh. What we can then do, we can basically take a symmetry of that mesh just to replicate the entire aircraft. So if it doesn't have any symmetrical loading on it, but the aircraft, the geometry itself is symmetrical about a plane, we can just create the mesh on one half, which is what we're doing, or what we've done, and then basically create a symmetry of that mesh about a symmetry plane. And then we can apply our asymmetric loading if we wanted to. Again, if you had symmetrical loading, then you might as well just create the correct boundary conditions at the symmetry plane. So the aim of the game is to reduce computation time. Okay, so if we just apply that, there you go, we can see the other side of the aircraft. So we want to try and reduce the amount of work we're doing as well. And then the other thing we can essentially do, we can add a clipping plane. So if we wanted to, we can basically clip through our model. We can drag a plane through our mesh. So if we just do that, there we go. And then we can basically run through our model and see the elements, etc. So inside. So it's pretty difficult to see if the mesh sealing of the ribs actually lined up with the top of the aerofoil, so you can actually see that in this view because we've clipped it. Okay, so that's basically the advanced meshing tool in a nutshell. So we've looked at linear analysis, but when is it not enough? Okay, so in this instance, we've basically got a buckle. It basically is exerted to large deformations. If we have a look at the linear assumption, we've said the higher stress, we've got a lower deflection. But with a nonlinear analysis, at a lower stress, we've actually got a higher deflection. So what the nonlinear analysis takes into account is the inelastic region of the stress strain curve, and it's also taken into account time. So for example, the linear assumption would make once the prong of a clip make contact with the center, that is it, that will give you a result. But nonlinear analysis will take into account contact and then sliding. So it's taken into account contact with the center of the part and then sliding along it. So perhaps this is a good time to see how many of you actually created nonlinear analysis before. So if we just run our poll again. So you'll just see a poll that will come up on your screens. Okay. It seems like a majority of you have never performed a nonlinear analysis before. Okay. Yeah. Hopefully this will be quite exciting. Okay, so analysis tools for nonlinear analysis. So again, we're still looking at CATIA V5 itself. So again, as I mentioned, we're referring back to this trigram. We're now moving away from designer and moving to design engineer. Okay, so it's still intended for designers, but we're moving towards a scale for design engineer. So we're still saying analysis experts can still perform nonlinear analysis, that's what they do, but we're just moving towards the upper end of the scale. What this means is we're now moving from CATIA V5, we're now taking components from a Simulia V5, so ATH, which is basically a thermal solver, ANL, nonlinear solver, and we're still using the CATIA V5 interface, but it gives us the ability to create nonlinear static analysis, thermal analysis, analysis using rubber materials, anything else, large deformations, etc., etc. Okay. So we're not focusing on Abaqus for CATIA yet, we'll come on to that in a second. So what exactly is nonlinear analysis? Okay, it's actually everyday situations. So everyday situations are actually nonlinear, without even us thinking about it. One of them would be coil spring compression. So when we compress, or when we go over a bump in our car, for example, and our coil spring compresses, that's a nonlinear situation. Flexing of a paper clip back and forth, so we'll come back to that in a second. Crushing an aluminium can so that it buckles. Again, once you crush it, it doesn't act elastically and spring back to its original shape. It generally buckles and stays at its new shape. So that's a nonlinear analysis. And hitting a pothole in the road as well. So we don't actually recognise it, but if we drive over a pothole in the car, our wheels actually exert quite large deformations. But it happens in such a short period of time. But it's basically acting elastic, so it springs back to its current shape. But again, that's a nonlinear case. But going back to the paperclip, if we move the paperclip with large deformations, let's say we apply that deformation about 7-8 times, eventually it will experience fatigue and then it will fail. So these are all nonlinear cases. So you don't ever expect it to flex it back and forth infinitely, and it always just spring back to its original position, which is what the linear analysis would assume. So here we have another demonstration. Basically all it is quite a short demonstration. It's a projectile hitting the door skin of a door, essentially. And this is going to be a nonlinear case, and it's time-based. So even though it looks like it's an animation, it's basically a time-based analysis. So you'll see the results as with respect to time. So you can see in this instance, as soon as it hits the door skin, stress basically dissipates and then is transferred back to that projectile before rebounding. Okay, so that was over time. You can see how the stress changes a lot on that skin. Okay, here we've got another example. So this is basically a rubber engine mount. Okay, and we're basically going to, because it's a hyperelastic material, we need to create a nonlinear analysis. So you can see perfectly elastic materials we'd assume would deform linearly, so have a proportional, the strain and the deformation will be proportional, but this is rubber, this isn't true. So we'll start off by creating a nonlinear analysis using an A&L component. Again, to simplify the model, we've taken, because the engine mount has two symmetry planes, we're actually using a quarter of the entire part. So we're just going to simulate the symmetry planes by adding no displacements along the y-axis and the x-axis. So that's what we're doing here. We're using displacement boundary conditions and saying no displacements in x and y on the corresponding faces. We're clamping the outer face because it will be fixed between a metal housing. And then basically at the center, what we normally have is a metal rod which is fixed to the engine that will fit through the center of this part. So we're simulating that using a virtual part. We're assuming that this metal rod will flex in the z-axis, so we'll translate in the z-axis. So we're going to enforce the displacement to our virtual part. And then we're going to view what result, or how that impacts our engine mount. The next thing is, because this experiences quite large deformations, it's very likely that it's going to come into contact with itself. So we do have to be a bit intelligent here. We do have to sort of understand, well, if it was to deform, how would it deform? And then where may it come into contact with itself? So we've selected the faces that we're assuming that are going to come into contact with itself. You wouldn't go and pick everything because it will take way too long to analyze and it just wouldn't work. And then we're telling it what type of contact we're expecting. So we're saying there's a contact pair, basically self-contact between itself, because it's just one part. Just define the mesh. So you're just going to modify the mesh size. Okay, and then we're just going to set up a job. So with an A&L option, we basically have more tools in order for us to set up jobs. So the reason for that is because we can run multiple jobs simultaneously. We can set up jobs and just leave them all running overnight, for example. So we just have more tools. Okay, so here's my job manager, and I'm just going to submit the job. So you can already see, rather than just run one job at a time, this is giving us more options. And the other thing we're doing, we're actually replicating the displacement in more to real life by actually applying the displacement in increments, so non-linearly. We're not assuming that just the displacement's applied in one go, we're saying that it's applied in time steps. And there we go, there's our results, so we can see the translations with respect to time. What we can also do at this stage is we can also change, so we're looking at the translation result, which CATIA calls an image. We can change our image generation, for example, to show maybe the contact pressure. So that's what we're seeing at this stage. So it's isolated all the other geometry automatically to display the contact pressure. Now we're seeing the von Mises stress. So again, non-linear analysis, this shows it with respect to time. You can see when it comes into contact with the bottom part, how the stress is transferred. Okay, so we're now again moving up the scale. So we're moved away from designer, we're primarily focused on design engineer. We're moving towards expert analyst, and we're going to have a look at Abaqus for CATIA. So again, we're still using the CATIA V5 interface. It's still familiar to any design engineer who creates models in CATIA. But we've basically got more capabilities than the ANL and ATH from the Simula V5. So now we have nonlinear explicit dynamic capabilities, network solving, so we could take into account calls from other machines to increase our computation time, composite layouts, bulk pretensions, etc. So this diagram is quite nicely basically illustrates what's going on. So we've got CATIA V5 where we're creating our models. We've got Abaqus, so Abaqus technology, not Abaqus itself, but Abaqus technology, bolting the two together, and we've basically got Abaqus for CATIA. So we've got the nice friendliness of CATIA V5, we've got the advanced technologies of Abaqus, put it together, and we've got Abaqus for CATIA. So what does that essentially mean? So we've got a table here which basically compares GAE, which is basically linear static analysis, FAX, which gives us some more advanced meshing options, and AFC, which is basically Abaqus for CATIA. So meshing, for Abaqus for CATIA, it basically gives us the same capabilities as FAX. Okay, so we saw them capabilities with the aircraft surface model. When it comes to properties, we've actually got an increased control over the properties with Abaqus for CATIA. So we've now got composite layups, imports from composite designs, more hyperelastics, we can analyze gaskets, etc., etc. Solving, so we've now got heat transfer analysis, thermal stress. So where with the GAE we only had one static case per CATIA analysis file, so we could only run one job at a time. With the FAX, we could run multiple analysis cases. We could still do thermal stress and parallel processing, but with Abaqus for CATIA, we can now actually do network-based solving, so we can send out to multiple cores, etc. Again, with post-processing, we now have non-linear specific results image, plastic strains, etc., etc. So you can see our AFC actually gives us a lot more capability. So why use AFC? So this is a nice little diagram which summarizes that. So in CATIA V5, we've got CATIA on its own. We've still got geometric associativity. We can easily create assembly constraints, and it's a familiar environment for the designer. But on Abaqus for CATIA, we've still got that same familiar environment. We've still got the intuitive assembly constraints, still got a geometric associativity, but now we've got a large catalogue of nonlinear materials. We've got contact, transient heat transfer, complete time history simulation, and so on. So in this demonstration, I basically want to show you guys Abaqus for CATIA using time-based sensors. Okay, so it's basically an impeller blade. The job's already been computed, so we're basically viewing the von Mises stress. We're looking at the results. Okay. We're basically going to create a Abaqus sensor for displacement. So we'll just show the geometric model. Okay, there we go. We've just hidden the result, so we can just see the geometry itself. And we're basically going to say measure a displacement at one point. So on one of the blades, there we go. We're going to select a point, and we're going to tell CATIA to measure the displacement in all its components. Okay. So as I mentioned, sensors are basically measurements. Because we created a sensor, we just need to tell CATIA to update, so it just reads the values. And again, it's plotting, in this case, the X deformation over time. Okay, so now what we're doing, we're going to actually add a secondary analysis into our analysis, so a secondary case. You can see it says Abaqus structural case 2. And because it still has the same boundary conditions, we're just going to copy and paste the boundary conditions. So it's basically clamped at the center. Rather than having to define everything again, you can just copy and paste any applicable loads, etc. But what we're now going to do, we're actually going to create it in our new case, the enforced displacement, which we're taken as a result from our first analysis. Okay. So we're creating a displacement at the bottom and at the top of that blade. And because a nonlinear analysis is time-based, we're going to take an iteration. So we're basically telling it at what iteration to set the displacement from. Okay, so we're setting this up as a parameter. We're not manually inputting values. We can get CATIA to do all the hard work for us. So we're creating the parameter using the formula editor. Okay, we just do a third component. Okay, we always try and utilize using copy and paste where we can. And there we go, so we've added the displacements. And you can see they're controlled using parameters now, so we can't manually go and modify them. Okay, so now if we run that Abaqus job, okay, again, we can rename a job as we like, because it's a good idea to rename them if you're running multiple jobs in parallel. Okay, solve that job, so in this case submit. And here are our results. Okay, so our rotational and translational and rotational displacement. So we can see that, animate that through time. It's a nonlinear analysis. See how that updates. Okay, another instance of using Abaqus for CATIA. So this is basically a thermal analysis on a brake disc. Okay. All we're basically doing, we've got a brake disc. We're going to assume it's clamped at the center, and we're assuming it being subjected to heat through friction when the pads clamp onto the faces. So we're basically creating a surface heat flux. Then what we'll do, again, we've defined like the material conductivity of thermal loads. And then run the analysis. So you can see over time how the heat changes within the actual model itself. You just clamp everything. There we go. Then we could feed that back into another analysis to get the von Mises stress. So we can take heat and then see how that impacts the model itself. Okay, so at this point, what I'll do, I'll pass it back to my colleague Alday, who will take you through what there is for you guys past CATIA V5. Alday?
Okay, thanks, Amit. Okay, as Amit explained, the final part basically is for high-end analysis. Like it's usually is more suitable for the analyst than the design engineer. Although, I mean, there is some overlap as well. Some design engineers tend to do some challenging stuff, and so they want to do a bit more what Abaqus for CATIA can offer. As you can imagine, Abaqus for CATIA, it's basically CATIA plugged in to Abaqus or vice versa, which means there are a lot of automation tools being set up for that, which means not all Abaqus functionality is going to be available to CATIA users. Therefore, the Abaqus option with CATIA associative interface is always there for people who wanted to have extra flexibility to do additional analysis. And now additional analysis, we will go through that in a minute, but you're talking about things like coupling between analysis, CFD, and so on. So basically, what is beyond Abaqus for CATIA? Why would anybody use Abaqus? It's basically, as I said, the flexibility. If you want to do multiphysics, where you want to do coupling between different analysis types, if you want to do CFD analysis, you need to do, for example, thermal and structural analysis. If you want to work out, for example, the fluid structural interaction type of things, then you would use Abaqus. If you want to do fracture mechanics, is excellent algorithm within Abaqus allow you to work out where the crack is going to propagate, such as the XFEM technique, and so on. And if you want to deal with, for example, advanced material properties such as concrete, soil, and all these complicated materials that don't behave like steel and so on. And more or less anything extra that's not available you can do more or less with Abaqus. Additional tools that can be, if you want to do, if you need additional tools such as, for example, you want to do advanced fatigue durability analysis, there is FESAFE available within the Abaqus portfolio. If you want to do non-parametric optimization using Tosca, that's actually structural and fluid optimization. If you want to do process flow automation and optimization, iSight is an excellent tool for that kind. Or if you want to do plastic injection molding as an additional tool available from that system to allow you to do that kind of analysis, as well as multi-body dynamics using the SIMPAC product. So you can see, I mean, basically it's scalable, whichever option you want to use. What is your role as an engineer, and so on. Then you can use the right tool for it. Okay. I think at this stage we are ready to go to our final part of the webinar, which is the 3D Experience platform. A lot of people wonder what it is. It's basically the latest development from Dassault Systèmes. So what is the 3D Experience platform? It's basically a platform that allows you to provide software solution for every organization or department in your company, such as, for example, from marketing to sales to engineering, all from within one single user interface. So it's basically a single easy to use interface. Usually powers 3D design, analysis, simulation, and intelligent software and collaborative interactive environment. This platform available on premise, public or private clouds, which has never been available in the past. So it's really, really exciting for a lot of people who want to get into that field. The way you would see, and you probably heard about it before, but the user will have access to what we call the campus. It's very famous nowadays. Basically, the campus allow you to run more or less everything from within it. So, for example, if you look at the campus, if you look at the west side of the campus, you have all the apps available for 3D modeling. If you look on the south part, you see all the simulation apps. I mean, obviously 3D modeling when we're talking about such as CATIA, even SolidWorks, Geovia, and so on. When you look at the simulation apps, things like the Simulia, the Delmia, and 3D-Via, and so on. If you look at the east part of the campus, you'll find all the information intelligence apps such as Exedit, which is the search and search-based applications, and NetVibes, and so on. The north part of the campus deals with the social collaborative apps, such as Innovia for data management, the 3D Swim, which is an excellent way if you wanted to look for information, and so on. So that's basically all from within one platform. If you really, I mean, today is not the best time, obviously, to go into too much detail about 3D experience. We will have later some additional specific webinars about it. But just to give a bit of idea, what is the key value of it, basically? It's really extend the reach for designers. It's almost no limit to what you can do with it. Whether you want to do simple, complicated, advanced stuff, you can do that from that. But that's what it offers the engineer all the capability they need, whether it's fatigue or fluid simulation and so on. That process also enhanced simulation workflow because basically one single user interface can be used to use or to do all the requirements for that particular company. Okay? Computation on the clouds, as I said, it's never happened before. Now it's available. If you want to do computation or visualization, all that can be done on the cloud. Okay? And finally, there'll be a migration for CATIA 5 analysis users. You'll be able to upgrade your simulation to the new path, basically. And the way the 3D experience platform works is basically slightly different to the current V5 situation. Everything's done, all the configuration is done through roles, basically. So, for example, if you're a stress engineer or a structural analysis engineer, then you license it based on your role, and through that, then you get all the apps relevant to your role, basically. So that way, it's easier for people to understand what they can do and what they can't do. So, for example, is another role which allows you to do more advanced stuff, such as advanced FEA modeling, fluid flow, and so on. So, like as I said, it's too difficult to go through everything today, but there will be a specific information provided in the next month or so about it. Okay. Just the final slide in here, just to show that the company can grow their skill and can grow their design and simulation complexity from that particular platform. So you can start from a single part to a full complicated assembly model, all from within one platform, which, like I said, it never happened before. Okay, there's more information about 3D experience. We'll be hosting a webinar at the end of May, a date to be confirmed. So hopefully you will receive an invitation for that. And also we have a confirmed date for a seminar in Coventry on the 18th of June. If you feel free to attend, if you have time to spare for that. Okay, I think that summarizes our webinar. We'd like to see if anybody has any questions at this stage. We have a few minutes maybe for questions.
Okay, guys, if you could type your questions, so we can't necessarily hear you guys. We'll read your question out and then answer them if you have any questions. So you can do that through your control panel. Go to webinar control panel.
It doesn't look like we have any questions at this stage yet, but please feel free to send your questions after the webinar if you like. We are very happy to answer them on your own time as well. So if you're in a hurry to go and finish work or something, please feel free to do so.
So we had one.
Okay. Yes, I think asking the question, will this be available to download? Yes, I think everybody who is registered or attended the webinar, you have an email with a link to allow you to see the recording of that webinar, just in case you've missed it or you want to follow it in more detail. Okay. I think that probably is the same thing. Like I said, we will have a recording of that webinar, and hopefully you will receive it when we compile the recording. Okay. If you don't have any more questions, are there any more questions? Okay, somebody's asking, do you have an office in Canada? Unfortunately, we don't, but as I said, we are the reseller for DASA system in the UK and South Africa. We would be very happy to pass your information to DASA system so they can put you in touch with somebody in Canada. I'm sure there'll be some representative of that, whether it's direct with DASA system or a reseller at that. So please feel free to send us an email so we can help you with that. Okay, somebody's asking what is the cost for these models on an existing V5 license. It's difficult to answer that during this webinar. What we might be able to do is to send you more details. I mean, obviously it depends on your existing configuration. There are some also special offers done for certain configuration, again, very attractive. So we can also send you that information. So if you do want more specific, please let us know your existing CATIA module configuration, and we will be happy to provide you with a proposal or even just a figure to allow you to get a feel of how much investment you need to add to get that. So no problem. We'll do that. Just please send us an email to follow that up. Okay, I think we're sort of slightly outside the range of the webinar. I'd like to first thank my colleague Amit for sharing this with me to do the webinar, and I'd like to thank everybody who joined us today. We will also send you some information about our next follow-up webinar. So thank you very much again, and we look forward to speak to you again in the near future. Thank you.
Thank you, guys.